Now what we're going to move on is to the next step. So now we're going to move on to a galvanic cell. So I'm sure you've seen these before as well. So if we have sodium solid, as you can see here, this is a redox reaction. You put them in together, sodium inside water goes boom. However, this is only chemical to thermal energy. This is a bit useless. As much as this is oxidation and reduction and redox, it's a bit useless because what are we going to do with that? Nothing. What if we wanted chemical to electrical? We would need to separate things. So what we need to do here is we need to separate things, because if we think about it, energy is actually the transfer of charge. It's the transfer of the cations. So it occurs by the electrons. So if we move electrons through a wire, we get electricity, and we move electrons in a redox reaction. So why don't we force the redox reaction to happen through a wire? That's where a galvanic cell comes in. We force the redox reaction to occur through this wire, and in doing so, we produce electricity. So, galvanic cells are in everything. Your phone has a galvanic cell in it. Your laptop has a galvanic cell in it. Your camera has a galvanic cell in it. Your watch has a galvanic cell. Everything has galvanic cells in it. Your car has a galvanic cell in it. It's simply any device that converts chemical energy to electrical energy. Anything with a battery in it is chemical to electrical. What's really important is that a cell is an individual galvanic reaction. It's an individual set that has this chemical, and a galvanic cell in it. A battery is lots of those cells together. So your phone will have loads of them. That's essentially how that works. So if we look at this before, we said oil rig. We said oil rig, oxidation involves loss, reduction involves gain. Now, we start to think about things called an anode and a cathode, and I'm sure you all know what they are because you've been through this before. But an oil rig cat is our new saying. Anode at oxidation, reduction at cathode. So it actually should be the other way. Oxidation at anode, reduction at cathode. So, an oil rig cat. I also like to think of it as an oil rig happy cat, because cathode is positive when we are spontaneously reacting. So, key terminology. We have two half cells. We have two electrodes. We have an electrolyte. We have an external circuit. We have a salt bridge. Now, in this example here, we don't have anything down. So I'll just say, if this is the positive side, if this is the positive side before, I said when we're spontaneously reacting. So I'm going to say this is spontaneous. This is spontaneous, and thus we have a positive reaction on the left side. The positive reaction will be the cathode, because the cat is happy. And what happens at the cathode is reduction. So what will be happening here is reduction. So this will be the reduction half equation. On this side then, it'll be negative. It'll be the anode, and it will be the oxidation half equation. Another way of remembering this is that you have consonants and you have vowels. That's another way of remembering it. The other thing here as well that I always like to think about is AO, Australian Open. Don't know why, I just always think about it. AO, Australian Open. It's just one of those things I always remember. And it's just how I kind of go about it. Now, one other really important thing that we will discuss in the next slide, but I think it's important we discuss it before we get into the example version of it. The salt bridge. Now, the salt bridge doesn't directly transfer electrons. However, if you pull that salt bridge out, it won't work. This whole thing will stop. There will be no electron flow between the circuit. Now, why is that? That's because these electrolytes need to be very neutral. They can have a little bit of charge, but they need to stay at a constant neutral charge they feel comfortable at. How do we do that? Because if we think about it, let's say in this example here, so at the cathode, we've got a positive charge. What are we doing? We're gaining electrons. So in this one here, we've got electrons coming in, and if we have electrons coming in, we've got, let's just say it's Zn. I'm just trying to think of an example off the top of my head, sorry everyone. So we'll have Zn2+. We have Zn2+ in here. As the electrons come in, the Zn2+ goes onto here and becomes Zn solid. Essentially, that's just what's going to happen in this example I'm giving you. What's going to happen is, with this 2+ charge becoming nothing, what's going to happen to the charge in this half cell? This is going to reduce. That's what that is going to happen. So that we're going to lose charge. This is going to become less neutral. It's going to become more negative. And this half cell is not going to like that. So what the salt bridge does is it has a molecule here. I like to use KCl, but there are a lot of other ones. You can use, actually no, I like to use KNO3, sorry. KNO3, I don't know why I use KCl. KNO3, and essentially what happens is the cations, which in this case here would be K+, get pulled from the salt bridge into this half cell. The NO3, which is the anions, get pulled from the salt bridge into the other half cell. And essentially what happens is, if you think about it, the negative goes towards the negative and the positive goes towards the positive. And they allow this to stay neutral. They allow both sides to stay neutral. And that is the role of the salt bridge. You take the salt bridge out, the neutrality is lost, and the whole circuit stops. You haven't got a complete circuit, it stops. So you need to make sure you have a salt bridge, and an appropriate one. KNO3 is a great one. So, example here. This is why I flicked across box. I needed an example. I don't know why my head was like, I cannot think of an example right now. Galvanic cell example. So we've got zinc, and in this case here, we've actually gone the opposite way. We've got zinc going from zinc solid to zinc 2+. In the other half cell, we've got copper 2+ going to copper solid. So in this case here, this one will actually be the anode, because the zinc is being oxidized, because this is 0, this is 2+, that is increasing, therefore we have oxidation. We also have an increase of Zn2+ coming into this space here. So what do we think is going to happen with that? Well, we need anions being added, as you can see there. We need anions being added because as we get more positively charged, we need anions to come and compensate for that. On the other half, we need cations. As you can see here, we're going to start to lose the solid here, and we're going to gain more solid here. Electrons, they're always going to flow anode to cathode. It sort of makes sense. They go from the negative side to the positive side because opposites attract. So then electrons will always go from anode to cathode. So always think electrons, they go from anode to cathode makes sense because oxidation involves loss. We're losing the electrons to the cathode, which is reduction, which involves gain of electrons. So think of it like that. So anode, it's the side of oxidation. It's the negative polarity in the galvanic cell. The cathode is the side of reduction. It's the positive polarity in the galvanic cell. Key point, polarity is on equal charge. The polarity is this here. The charge within this is where we talk about the cations. They're slightly different concepts. What's really important as well is the concept of anode and cathode, and you putting something there and saying that's the anode or that's the cathode. So notice before how in this example, zinc was being oxidized. And if I go back here, I said here that zinc was actually being reduced. That's because they can do both. Like most of these things can do both. It just depends on what their partner is, and we'll discuss that in a little bit. What the important concept I'm trying to get at here is that when I put this here, when I put this big chunk of zinc here, I don't say that's going to be my anode. What I say is that is an electrode. Essentially what's going to happen at that electrode is whatever I put in here and whatever I put in here is going to determine whether that is an anode or a cathode. The anode is only where oxidation is. If oxidation is occurring, the electrode becomes the anode. If reduction is occurring, the electrode becomes the cathode. You call it an electrode, and then once something starts to happen, you give it a name. So it's like saying you have a park, so you have a big park. I play cricket there, it becomes a cricket ground. I play football there, it becomes a football ground. I play soccer there, or football still, I call it soccer/football field. Like, It's the same spot, but as soon as I go and do something on it, I call it that. So, you know, if I go and play lacrosse on it, I call it a lacrosse field or hockey field or whatever you want to call it. Whatever sport I'm playing on it, I'm calling it that. Same thing applies to galvanic cells. If that electrode is placed and it starts going through oxidation, I call it an anode. It's not an anode before that. It's only an anode when oxidation is occurring. If oxidation stops occurring, it's just an electrode. That's really, really important. And it's a really important terminology when it comes to VCAR questions in how you sort of write your questions and how you answer your questions. So, galvanic cells. As you can see there, it's to prevent electrodes from becoming charged. Cool. That's what we've already discussed this stuff. The one thing here that we haven't discussed is that the material used in the salt bridge needs to be unreactive and highly soluble. That's why KNO3 is a really good example. Awesome. So, if you have a direct reaction, you get thermal. If you have a galvanic cell, which is an indirect reaction, you get electrical energy. We like that, and that's what we want. So, here we have a very cool galvanic cell. Now, why is this a cool galvanic cell? That's because we have an inert electrode. Now, what I mean by an inert electrode, if you have a half equation here where a gas is formed, and a gas is essentially what your electrode should be. That should have been your electrode. But in this case here, we have a gas. You can't really have a gas as an electrode. So we need to make it work as an electrode. So what we do is we have this cool device where we put an inert material as the electrode. So the inert material is usually like graphite or platinum. These things don't react. However, they can act as a catalyst to a reaction. They can act and allow something to act in its place as the electrode, whilst it just is the physical electrode there. So, in this case here, I like to think of it as, I'm not sure how many of you sort of I follow the NBA quite closely, and in the NBA, a lot of their stadiums over there, they can convert them overnight from a basketball court to a hockey stadium. A lot of the ones closer to Canada will do that. So I sort of think of it like this electrode is the stadium, and then the gas is like what we're putting on the court. Are we putting a basketball ring there, or are we putting a hockey stadium, like a hockey court there, or whatever they call it, hockey ring, is that what they call it? Essentially, that's kind of how I think about it. So I'm just trying to refer to real life examples. You have a stadium, and then it depends on what you put down as to what you play. So what gas am I putting in there is what's going to act as my electrode. So in this case here, the hydrogen gas is acting as my electrode, even though I have an inert electrode in there, which would be, platinum, or it would be platinum or graphite. And we call the platinum or graphite the cathode, even though the reaction is occurring through the H2 gas, because that's what the physical thing is there. Now, my second point with this one here is you notice how instead of a light, we've put a little meter. And that little meter is pointing this way, which means that the current is going that way, which is what's happening, or the electrons are going that way, which is what's happening. The electrons are going that way. So the electrons are going from the anode to the cathode. And then it says here, negative 7.6 volts. That's how I am determining its charge. I'm determining what's going on. So it's negative 7.6 volts. What's really important is the negative refers to the direction. It's like our delta H's from before. You cannot have a negative voltage. It doesn't exist. That is still 0.76 volts. It's just that it's heading in the opposite direction to what the reader reads in. So this thing is like a voltage reader. It reads in this direction. So when the charge goes this way, it says, oh, I'm in the negatives. It's negative 0.76. But it's actually just a positive voltage going the opposite way. So it's just the direction of the voltage, really important. So it's a 0.76 voltage. And you'd say, how did you determine that? Well, we can determine that, and it's actually quite easy to determine. So a galvanic cell is able to generate a current, and as the electrons move, we say that the potential difference exists between the two half cells, and that potential difference gives us the voltage value. So we can measure the potential difference of a single half cell called a standard electrode potential. And we do this by connecting every half cell to a standard hydrogen half cell. So if we compare everything to a hydrogen half cell, we can say this is what the standard electrode potential is. And so as you see here, the zinc half cell is a negative 0.76. As you can see here, we have the PB one, and the PB gives us negative 0.13. So our lead one here. So our lead gives us negative 0.13, but our zinc gave us negative 0.76. Thus, we conclude that lead is a weaker reductant than zinc. And we'll discuss that when we get to, where is this? Yeah, here. This is the other slide. I was like, wait, is there another one? And then as you have here, we have silver versus hydrogen. We get positive 0.8. What that means is that our silver is actually on the opposite side to our hydrogen. And it has swapped things. So in this case here, back here, our hydrogen was always the positive cathode. It's actually become the negative anode. And the silver has become the positive cathode. So what I mean by that is this here. This hydrogen is the standard, it's the middle. It's 0.0. Why is that? Because if we compare hydrogen with hydrogen, nothing happens because they're the same thing. So if you look at this here, you have the strongest oxidant, you have the weakest oxidant, you have the weakest reductant, you have the strongest reductant. What that means is that this here is always going to cause everything to be reduced that it goes with. It wants everything to be reduced. Whereas this one, wants everything to be oxidized. Wrong language. This thing wants everything to be oxidized. Everything that goes with it is going to end up being oxidized. On this case, the lithium solid, it wants everything to be reduced. Anything that goes with it is going to be reduced. These two are highly reactive because they're at the bottom ends, at the top ends of their strength. Whereas these two are the opposite. They're really, really poor at causing other things to be reduced and other things to be oxidized. And as you can see here, this is from your data booklet. These are the values that were obtained when comparing with the hydrogen half cell at SLC conditions. And as you can see here, these ones were positive, these ones were negative. So these ones just went in opposite directions. When these ones were in here, this was the cathode. When these ones were in here, this became the anode. It just depended on the strength comparative to it. And what we can utilize from this is we can figure out our value. So we can figure out how much voltage are we going to get out. So when we compare the hydrogen with the nickel, we get 0.25. But what if I compared the nickel with the copper? Well, what you look at is the difference. Well, if I have 0.34 and I have 0.25, what you do is you technically take away the 0.25, but because it's a negative value, you end up adding it on, and you get 0.59 as your difference between those two cells. So you're going to get a difference of 0.59 volts. So that's what you're actually going to get when you compare those two. And that's how we determine what we're going to get out and how we get our electrode potentials. So we've seen that the following reaction will be able to be used in a galvanic cell to generate electricity. So what if we replace Cu2 plus with Mg2 plus? Will we still be able to generate electricity? No. Why is that? Because we need to look at our series. So if I have zinc solid and I have copper 2 plus, I have top left, bottom right. So I have a really strong oxidant and I have a really strong reductant. Tick. That's going to work. That's going to be spontaneous. We're happy with that. If I have Mg2 plus, I have a really weak oxidant now. And I still have a strong reductant, but my weak oxidant isn't going to be strong enough to deal with the zinc solid. Therefore, from going bottom left to top right, that's not spontaneous. I'm not going to get a reaction occur. There will be no spontaneous reaction occur. If I want this to happen, I have to force it. And that's not what we're looking at here. We're looking at what will happen spontaneously. So Mg2 plus to Zn solid is not going to happen, whereas our Cu2 plus and Zn solid will happen. And it's the top left, bottom right. Now, what if we have multiple things? Well, what we talk about here is we always choose the strongest. So even if I had this as well, I would choose this over this, and I would choose this over this. Because, other way around. Because that one is the strongest oxidant and that one is the strongest reductant. So you always choose your strongest reductant and your strongest oxidant. So top left, bottom right, and you always go highest left, highest on the right, or lowest on the right. So again, the other thing is SLC. We've already discussed SLC. You have to be at SLC. Really, really important. This was all done at SLC, so we need to be at SLC. And as we talked about before, calculating. So we do our E of our oxidant, take away our E of our reductant. Why is that? Because we always end up with a positive value. We should always end up with a positive value. When this one is higher than whatever one you're doing, even if it's two positive values, so you have 0.8 and you have 0.15, well, you need to take that away to find the difference. So you take 0.15 away, you end up with a difference of 0.65. Whereas if you take away a negative value, you end up adding it on. So you end up going 0.8 plus 0.13, and you get 0.93. So you always end up with a positive value when you use this equation. So this is the voltage of the cell, or the potential difference of the cell. So the potential difference. That's what we're looking at. The potential difference of the cell. Awesome. So we have a practice question here. I want everyone to have a go at this and see how you go. So essentially what we've got is a switch is being flicked on and it allows for flow through the circuit. Which of these will have the electrons flow towards it? So which way do electrons flow? Remember we mentioned it a couple of times. And what is the potential difference between the cells? So have a go at this one here. I'll give everyone maybe one more minute. Minute and a half again, total. Probably fair for this question. How much we got left? 15 slides. All right. All right, so we're going to go through this one, and then I was just looking at what slide. That's why I've got my phone. I've just got the slides off my phone. We have about 10 slides on fuel and secondary cells. I think we're going to skip over that. I think we're just going to run out of time, sorry. But there wasn't a lot of detail on those. They were very much just like a very brief starter. So don't worry about that. We've gone through a lot of content today. Like we've gone through probably nearly a whole term, maybe a little bit less than a term of content, which is a lot of content considering we've been through in like 2 hours. Then we'll go over some tips. I think the tips and advice are really important at this point. So we'll go over them quite quickly, and then we'll jump into the practice questions jump into the questions just at the end. So go through this question here. First step, figure out what is the anode, what is the cathode. So you've got copper and you've got copper. So you've got, where are we? We've got copper and we've got copper. We have Fe2 plus, Fe3 plus. So we've got Fe3 plus, Fe2 plus, and Fe2 plus down here. But we don't have Fe solid. And platinum's not in it. So it's going to be this one, and it's going to be this one. So if we think about it, we've got, as you can see here, we've got the cathode and we've got the anode. So I'll get rid of my scribbles because my scribbles are just going to complicate things with there are already scribbles there. So we have the anode and we have the cathode. So anode and cathode, we have electrons flowing from the anode to cathode. That's how they always flow. So therefore, it's not going to be the copper electrode. The electrons are always going to flow towards the platinum. So we're left with C and D. Then we need to do the maths. 0.77, take 0.34. It's going to be 0.43. So we end up with C. And that's how you go about that question there. So it's a very typical practice exam or sort of typical VCAR multiple choice question. So that was from 2015, so it's a bit older. But as you can see, the exams back to 2015, 2014, 2012, they're all very relevant. They all still very much have very similar content and are quite useful in your study. So I think that's just an important point. So there's another practice question here, and there are solutions to it. You're welcome to go through it if you'd like. It's from 2008. That's how old these ones are, and they're